If the atmosphere, especially over water, is made up of zillions and zillions of tiny convex drops of water, then collectively perhaps they all combine to make one big convex lens, in which case it would act like a magnifying glass. Okay, so with that in mind, let's look up some websites dealing with the refraction of light. You might see a graphic something like this, showing light bending downward. Just water's flat, it always seeks its own level, and we're looking across a flat plane of water, 46 miles across. Check this image out right here. Now, I caught this image shortly after Rick and I returned from our trip across the lake. This image is extraordinary. Okay, the boat right here, I'm going to guess, is less than a mile away. I shot this image from right about here. This is where we were looking across, and this is the area right here where those people were walking. And the boat, as you could tell by the size of the people on the boat, wasn't too much further beyond that. So maybe a half mile to a mile, or at the most, I would say, away from where we were. All right, now when I was headed back to Chicago to catch my flight, I snapped this picture of the Willis Tower. And this is, if you go on Google Earth, this is right about the area right here where I believe I was when I took that picture. Looking across, it's only about 0.6 of a mile. So I'm just a little over a half mile away, and look at the size of the tower as compared to the car that was diagonally in front of me. We were looking at the Willis Tower from this direction right here when we were on the other side of the lake. Now, okay, so let me slide the car over and shrink it down to the appropriate scale beside the boat. Do you see something rather interesting here? This building is significantly magnified. The image on the left shows the size and scale of the building next to a car at 0.6 of a mile away. The image on the right shows the same building and the same car with a boat at 46 miles away. The atmosphere really is acting like a lens. What type of lens? A convex lens or a magnifying glass. So I'm going to suggest this is what's happening. The atmosphere is acting like a lens, which magnifies the city, brings it up a little closer, and as it does so, we start to lose a little bit of the bottom of the buildings, and perhaps due to the density in the atmosphere, there's additional refraction that takes place that makes it drop down even more. Let's just go back and hear from the experts once again what's happening with the atmosphere.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here, just maybe now you can just see the top of the Sears Tower, and if our simulated temperature inversion moves into place, hopefully now you can see pretty much all of Chicago,
see all the lower buildings,
including what's at ground level.
So the atmosphere really is acting like a lens.
Yes.
So the atmosphere really is acting like a lens, according to the experts. Now, you guys don't need to go out and spend tens of thousands of dollars to get that pretty piece of paper to hang up on the I Love Me wall and put letters after your name so that you can call yourself an expert. You can be an expert with what you see here on the screen. Yep, believe it or not. Then find a table and a chair. And okay, you're going to bend the paper so it looks something like this. Tape the lens to the table, get a chair that's about the same height as the edge of the table, put your iPhone on the end of the chair, and the chair will act as a dolly, so you can just kind of pull the chair back, and looky here. Look what happens with atmospheric lensing. Wow, isn't that amazing? And you didn't have to go to college either. Now, you can get in a boat and whee, drive to Chicago, and wow, look at that. Now, let's compare. See? Look at this. This is how much of the city was lost simply due to atmospheric lensing. Now, remember, the experts, the guys that spent tens of thousands of dollars to get advanced degrees in this stuff so that people would recognize that they're smart, they told you the science really is that of a lens. Here's an interesting video I saw online regarding a full day time lapse revealing superior mirages. Now, this is quite extraordinary, actually. This is from skunkbayweather.com, September 7th, 2012. Notice the buildings and the shoreline here over on the left. Keep your eye on that. Just watch that, and the mountain in the background. Everything's pretty cool. You can see pretty much everything there, but as the day progresses, and we are now at 9:30 a.m. and it's 59 degrees, 60 degrees, it's getting warmer, the temperature is changing, we start to see some miraging take place, right? It starts to distort things a little bit. Ooh, look at that. The water seems like it's getting higher, and we're losing buildings, and we're losing the beach. Here it is now, noon, 63 degrees and climbing. Uh-oh, there it goes. Oh, there it is again. Oh, it's all miraged. Huh, it's all distorted. Sometimes you see it, sometimes you don't. The default is to see it, though. That's the point. The default is minus distorting atmospheric conditions, you would be able to see everything clearly. But due to different temperature variations and density in the atmosphere and whatnot, sometimes you can see the whole shoreline and the buildings, sometimes you can't. But the magic trick is not in being able to see it. It's what is taking place that obscures your ability to do so. Look at the comparison right here, just in these two images right here. The one on the right at 5:44 p.m., 63.5 degrees Fahrenheit. Can't really see anything on the left shoreline there. And on the left at 9:43 a.m., when it was 59.5 degrees Fahrenheit, we can see the shoreline, we can see buildings, trees, all kinds of stuff. So, I mean, either this lake is, filling up and draining so that the water level is higher or lower, or it's due to atmospheric lensing and distortions, refraction, and all that good stuff, causing us to not be able to see it at certain times. I think that's exactly what's going on Lake Michigan. And again, based on that imagery that I saw looking 46 miles across versus 0.6 miles across, I really do believe that, just like the experts said, the globalist guys, these are people who believe in the globe now, they are the ones that said, hey, the atmosphere really is acting like a lens, and they put a lens in front of the camera to show how it works. So I'm just doing what they're doing. I'm using the same logic that they're using, the same science that they're using. And, science is all about testable, observable, and repeatable data, right? So I went on Amazon and I got these plastic magnifying sheets and came up with another way of doing the same thing using the sheet right here. Set the city up, a little cutout of the city, and now I've got the big magnifying glass sheet. Bring the camera right up to the lens. See, that's the normal view of the city. Now let's back up again.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here,
The atmosphere really is acting like a lens.
yes.
Atmosphere really is acting like a lens, and this is how much of the city is missing due to the lensing effect, the magnification of the atmosphere. And as with any scientific experiment, you always try to improve upon what you did before. So I got some foam core, made a little housing for the magnifying sheet, and pasted the city on the back there, and I made it as two separate pieces so that I could flex it as necessary, because I think that there are different types of atmospheric conditions that would allow for more magnification versus less magnification. So in this scenario, you have more magnification, and in this one you have less. And for this one I decided to put the Toronto skyline into my little box here. And let's try it again. Okay, we're all the way up against the glass. Now let's zoom across the lake. And wow, look at that. The lower portions start to disappear. Now let's zoom back in to get a little closer to the one that Captain Baltard was talking about here. And wow, look at this. Here's his image on the right, and here's my image on the left. Missing the lower portions of the city had nothing to do with curvature whatsoever. So thinking about all this, and thinking about what I had just shown you regarding atmospheric lensing, magnification, refraction, all that, with regard to cities and objects at a distance on the land, I got to thinking, I wonder how this would work with the sun and moon. So this is what I came up with. I've got my magnifying sheet frame, and I created a little stand to paste the sun on it and keep it the same height over the flat surface of a table. So the sun is always going to be parallel with the surface. And check this out. All right, here's the first test of a sun moving over a flat surface, and with no atmospheric magnification, it does what we might expect it would. It gets smaller as it goes away from us. All right, now let's see what happens when we add in our atmospheric magnification. Again, water and refraction. Water causes magnification and refraction, right? So let's bring the sun back. Oh, check this out. Refraction bends the light downward. It made the sun set on a parallel surface. As it was moving parallel, the same height, the whole way over a flat surface, the refraction caused the sun to set. Not only that, well, let's bring in the beginning of that little test, and we see that it maintained pretty much the same size too. Pretty close. And of course that's because as it's moving away, the magnification is still taking place, and so even though the sun's further away than it was in the beginning of the test, the magnification basically preserved the same size, and the refraction made it set. Of course, again, depending on how much moisture is in the air, we could see that the sun doesn't appear to change in size at all as it goes down. We could see sometimes perhaps that it looks like it's getting bigger when it goes down. You ever see like a really big sunset or moonrise, moonset, you know, where one of them looks really large on the horizon? Well, that could be because there's lots of moisture in the air causing that effect. Or when there's less moisture in the air, obviously you won't have as much magnification taking place, and so it looks smaller as it goes away. So it's all relative to the amount of moisture that's in the air. Now, I'm just going to put forward a crazy idea for you to think about. And that is, if Rob Skiba could figure this out, I'm just going to go out on a limb here. I think it's quite possible that the creator of the cosmos could have figured out the same thing and engineered our beautiful sunsets, thanks to all that water he placed in our atmosphere. Just something to think about.